Hello, welcome to today's video where we are taking a look at how to do differentiation by first principles for trigonometric functions. So therefore, I'm expecting people coming to this video already knowing or having a basic idea of how to do differentiation by first principles to more easy functions. So things like polynomials, so that's stuff like x squared. And therefore today we're basically building on top of that by looking at more weird things, I guess you could say, like trig, which would be, sine of x, cos of x, that sort of thing. Also, a bit of a disclaimer, I'm approaching this video from the point of view of it being a tutorial video, which you might have already guessed by the format of this title screen that you can see right now, to make it in line with my other tutorial videos, but therefore it's distinct and different from my extension videos such as the Prove It series and the Can We Do That videos that I do, where we're more focused in those videos on why things work the way they do and really exploring maths, whereas in this video we're very much sort of keeping to what you need to know in order to be able to do the things you're meant to do for an exam. So therefore, please do forgive me because it means at certain points in the video I am going to be brushing over certain facts just because I will be very much keeping to what do you need to know for the exam, and I will have a future video in my Can We Do That series where we'll focus on why certain facts that are established in here are true. So do watch out for that when that is made. So, a quick reminder, which is that differentiation by first principles is a formula, and this is the formula that it is, and actually this formula is in the form booklet. Hopefully you're already aware though why this formula is true from when you first came across differentiation by first principles for the first ever time. And let's just get straight on with the example because that's the easiest way to show this stuff. So we've been given the results that the limit as h tends towards 0, which by the way is what that lim h with the arrow and the 0 means. We've been given that the limit of sine of h over h as h tends to 0 is equal to 1. And also the limit as h tends towards 0 of cos of h minus 1 all divided by h is equal to 0. So we are allowed to use those facts in the question, and interestingly these two facts being given in the question is kind of basically the whole main reason why I did that disclaimer of this being a video for learning how to do stuff for the A-level exam rather than one of my proof videos, because it seems for the A-level exam, looking at previous exam questions, you don't really ever need to, it seems, justify why these two facts are true. They're generally given to you in the question and you can just use them to do the proof without having to know why they are true. But that's a bit unsatisfying, so if you are somebody who likes to understand why these things are true, I will be making a future video in the Can We Do That extension series covering this stuff. And in fact, if you are watching this video far into the future, when I've actually made that video, a link to that video should hopefully appear on the screen right now if that video exists. But anyway, for the purposes of today, we're just interested in doing this proof for A-level study. So therefore we're just going to use those facts to prove that the derivative of cos of x is equal to minus sine of x. So to do that, all you got to do is apply the differentiation by first principles formula to cos of x. Cos of x is the function we're differentiating, so that's the f of x. And of course the differentiation by first principles formula, as we saw on the previous screen, tells us to do the limit as h tends to 0 of f of x plus h, which means our function with x plus h plugged into the function. So that means, as we've only got an x in a single place, that's quite easy to do here. Literally just replace x with x plus h. And then subtract f of x, which is, for us, just cos of x. And then divide that by h. Cool. Really important you are not sloppy with your notation. You need to set this stuff out exactly the way I'm setting it out here. If you don't, you are risking losing marks. So that's something to bear in mind. People sometimes start forgetting to write the lim notation or getting letters wrong and all that sort of stuff. And if you do that, you are risking losing the marks because this is a proof question, so they're going to be very picky on everything being mathematically correct. Cool. So what are we going to do now? Well, the problem is we're looking at this, it looks a bit scary. We're going to want to simplify it. And the way we're going to do that is we're going to want to try and rewrite the cos of x plus h bit. Because at the moment, subtracting cos of x from it, we can't really do much with that in its current format. Nothing is really cancelling out there or in a format that allows us to simplify it. So therefore, we're going to use the compound angle formulas, or addition angle formulas as sometimes called. Of course, a reminder, those are in the form booklet. I'm talking about the cos of a plus b formulas. So therefore, we can use that to split up cos of x plus h, because also, by the way, a little quick reminder, of course, cos is not a number, so you can't just multiply out the brackets. So that's why you have to use an identity. So therefore, cos of a plus b is cos of a, cos of b, so in this case that would be cos of x, cos of h, minus sine of a, sine of b, so in this case that would be sine of x, sine of h. Cool. And then we're taking away cos of x. Nice. And that's still all being divided by h. Still writing the lim notation because we haven't done anything with it. It's got to stay there in the notation throughout most of the question until we've applied it, because it's basically an action. It's telling us to do that notation. So until we actually do that action, we need to still write that notation to remind us to do the action. But anyway, the next stage we're going to have to do is we're going to have to do some more rewriting. And what we might choose to do is we might start to choose to isolate the h's from the rest of the stuff. And to do that, we're going to need to do some factorizing. But in order to even be able to do that, we're going to want to split things up a bit more, because we notice that there's two terms which have got a cos of x in them. So it'd be a good idea to group those things together. So I'm going to write cos of x, cos of h, and then I'm going to write the minus cos of x right next to it, just because that'll make it super clear what I'm doing in the next step. And then I'm actually going to already put that over h, because what I'm also going to do while I'm doing that is I'm also going to split the fraction into two separate fractions, using the fact that there's the minus sign in front of the sine x, sine h, because that will allow me to then write this first fraction I've written, subtract sine of x, sine of h, all divided by h as well. That common denominator has got to spread across both of these mini fractions. Cool. Now the reason we've chosen to do that is because now we can take a factor of cos of x out of that entire first fraction. So therefore, we can write cos of x out the front of that thing. So I can write cos of x like that, and therefore that will leave behind cos of h minus 1 all over h. Because of course, a reminder, whenever you multiply a number by a fraction, that number effectively just multiplies only the top. So that's why we're allowed to bring that cos of x out the entire front, not being even in the fraction at all now. And similarly, although it doesn't change as much here because we're not having to really factorize stuff, I'm still going to bring that sine of x out the front so it's not part of the fraction. And moving across to here, so we've got more room to lay out the next steps. Then the next step is something that some people sometimes might be lazy and not bother to write, but I think it's a good idea to write if you want to ensure you're getting all the marks. Doing a proper proof where you're not leaving anything unclear is always a good idea. And basically what it boils down to is the fact that we're at the point where we now are kind of wanting to apply the limit, I should say, part of this problem to the expression we've got inside those brackets. But the thing to be aware of is that this is the lim as h tends towards 0. That means from the point of view of the limit, h is the variable almost that we've got here, whereas the x is kind of not affected. Although x is a variable technically, from the point of view of the limit notation, it's kind of like just a constant, like a number out the front, because as h varies, x just stays as what it was before, which is just x. So therefore, what we can do is start to reflect this in the notation to make it clear the lim notation is only affecting the parts that have the h in. So we can, for a start off, just like with differentiation and integration normally, split it up using the fact there's the minus sign in between the two sort of halves of what we've got, but then also almost factorize the cos of x and sine of x out the front of those two separate limits. So what I'm saying is write this. We're going to have cos of x, lots of the limit as h tends towards 0 of cos of h minus 1 over h. And then similarly, we're going to have minus sine of x, lots of the limit as h tends towards 0 for sine of h over h. And as I said, that's to illustrate the fact that x is not going to be affected by h changing. Only the h's are going to be affected by h changing. And it's at this point that things are now very interesting, because we've now decided to write our thing in the way that we have. We might notice that the two things that the limit notation are applying to now are just the things that we were given in the question, the results that were given in the question. So therefore we can apply those two results that the question gave to us. We don't need to know where they come from, but we are allowed to quote them because the question said so. So therefore, the limit as h tends towards 0 of cos of h minus 1 over h was, according to the original question, just equal to 0. So therefore we've got cos of x times by 0. So I'm going to write that. I'm writing multiply as a dot in case you've never seen that notation before. That's what that dot means. And I'm just doing that so we're not having the times symbol as a cross, which could be confused with my x's. And then similarly, we've got the limit as h tends towards 0 of sine h over h. That, according to the question, was 1. So we also similarly have 1 times by sine of x over here. And therefore, that's really interesting because we've got 0 times by cos of x, 0 times by anything is 0, and then we've got minus 1 lots of sine of x, which is equal to minus sine of x. So that is why cos of x differentiates to minus sine of x. However, there is one final thing I do recommend people do when doing a differentiation by first principles question, trying to lay it out as a proper proof, fully justifying everything. In some ways a bit less necessary for this question as those results were directly given the question, but it's just good habits to get into. It's good to justify why this step happened. So therefore I would write because, and then writing that basically the two facts that were quoted above, basically just pointing out I know what's going on here, why it's true. Never hurts to show off your knowledge in proof questions. And then another thing that never hurts to do for proof questions is to have a proper conclusion. Even though our result has ended up being exactly what we expected it to be, it never hurts to confirm that you know that we're done, and so therefore it's good to have a conclusion that illustrates that. So here I would have my conclusion, which is therefore confirming the fact that they wanted us to prove. Therefore, we have confirmed that the derivative of cos of x is minus sine of x. So there you go, that's applying differentiation by first principles to prove the derivative of some trigonometric functions. However, you might want to be trying this stuff yourself. So to give you an idea, here's another couple of questions you might want to try yourself. So we have done the example where we prove what cos of x differentiates to, and you might want to try and prove what sine of x differentiates to, which I must admit is really very similar to the question we just tried, but therefore good practice to put into action the things that you've just seen. And on top of that, interestingly, another one you could try that I've got written here is proving that e to the power of x differentiates to e to the power of x. As of recording this video, they've never done that before, and that's because, this lim result here, even more crazy to accept based on Maths A-level knowledge, but again, this is something I would be looking at in a future extension video in more detail, but for the moment, you can definitely try this as a practice question. A similar idea, you're given this result and you just have to accept it and use it as part of the question without having to really know where it comes from. And that is the final thing I wanted to say. So therefore, hopefully you found this video useful. As I said, this was more focused on what you need to know for A-level exams. But if you're interested in knowing why things happen, check out my Prove It series and my Can We Do That series, because there will be some videos talking more about the idea of differentiating things by first principles in those particular series. So do check them out. So goodbye.